All right, how's it going, everybody? Happy Monday. We're starting week 2 here. This week we're going to be wrapping up our chapter 1. We're going to do sections 1, 3, and 1, 4 today. Tomorrow, for the other half of week 2, we're going to begin chapter 2. That'll be looking a little bit more at our histograms, doing a little bit more computation here. Finally, we've been doing a lot of vocabulary type things, and that will sort of continue here today. We are going to look at a little bit of some numerical do's and don'ts, certainly with our frequency tables here. But again, today will still end up being relatively vocab based, at least compared to some other things that we're going to see later this semester here. So um, let's get started here with section 1.3. This is going to be the place we're actually going to deal with numbers a little bit right here. And I do want to say I'm going to have my calculator here available to help me out with some calculations. You've got access to about 1 billion different calculators if you're sitting in front of your computer or on your smartphone, so I expect that you should be able to do at least our basic operations here. Whenever we need to do anything super fancy in our calculator, I'll certainly be sure to let you know, but for anything that's a basic computation as far as like addition, subtraction, multiplication, division goes, I very much assume that you guys are capable of handling that kind of stuff on your own here. So let's get started with section 1.3. In this section here, we're talking about frequency tables, and levels of measurement. And right away, I guess the first thing I'd like to say is we're not going to really talk much about the levels of measurement here. I gave you guys sort of a little statement, a sentence about that in your weekly guide that I think that you should be able to read through that section and understand the distinctions that they're making. But I am certainly more worried about our classification of variable as numerical, categorical. If it's a numerical variable, discrete or continuous. If it's categorical variable, it is either nominal or ordinal. It's just a name, or it is an ordering of categories here. So so really, I'm interested in frequency and frequency tables for section 1.3. So we're just going to look at an example and make sure that we understand all the vocab that's associated with each of these tables here. As you can see in our sample table that we're about to fill out, there's 3 columns that have the word good in them and 1 column that has the word bad in it. Again, this is sort of our do's and don'ts of frequency tables. Finally, we'll draw some graphs that are going to be associated with this frequency table, and we will draw some conclusions about those graphs. Before I really get started here, I'll say another one of our goals today is going to be to decide what conclusions can we draw in what situations. And one of the big things that happens in this statistics class is that since the goal of the class is for us to make decisions, I very often end up with students that get very excited about the conclusions that they're making and then kind of overstate what it is that we know. A very careful thing about this class is wanting to make the strongest possible conclusion without overstating what it is that we know. So kind of landing in the sweet spot of truly saying what it is we do know without saying anything that we can't say for certain here. So balancing that is really important. So a lot of the things we'll talk about today is saying what conclusions should we be drawing from this certain scenario. So let's take a look at our first scenario here today. Suppose that researchers sample 120 people, and all of the 120 people sampled have had chickenpox at some point in their life. So they're only sampling people that have had it. All they're asking them is, at what age did you get chickenpox? Chickenpox is classically something that most people only get once. The medical advice associated with chickenpox has changed over time due to our access to things like vaccines. It used to be a long time ago that people would intentionally get their children chickenpox. And relative to the health benefits associated, that actually might not have been a terrible idea a long time ago. Now we've got vaccines for things that makes that not necessarily a very good idea at all. So science has changed, and that's made our medical suggestions change here. So different people get chickenpox at different times. Lots of people get it when they're a kid. Other people get it when they're adults. And very importantly, chickenpox is one of those diseases where the symptoms that you experience change quite a bit depending on the age at which you get the disease. So in this case here, even though researchers might be asking people, what age were you when you got chickenpox? What the researchers are really interested in doing is lumping people into the age group category associated with the symptoms that they're going to end up experiencing here. And so the results are given in this table, right? So they've taken all these age ranges that might be associated with what the medical community understands are the different age categories or classes, age classes that are associated with different symptom sets for the disease. And out of the 120 people that we sampled, we should be finding that this is all 120 of them accounted for here. And let's just do some quick math to make sure that's going to check out here. First, I'm going to add up all my tens. 30 and 40 is 70, plus 20 is 90, plus another 10 is 100. So I've got 100 in my tens. 6 and 8 is 14, plus 4 is 18, plus 2 is 20. So I did get 100 when I added my tens. I got 20 when I added my ones. And so I'm adding, by the way, there's an extra row in my table here. I'm going to fill out some additional information. And so here, I kind of want to make the statement, start getting us used to some variable letter names here. Here we would say we have a sample size of 120. A lowercase n is always going to be our symbol for sample size this entire semester. All lowercase n's is referring to the number of observations that we have in that sample. So in this case, I would say that we have an n of 20, and that's very, very common verbalization of that as well in statistics. You can literally just say what your n is, and people understand that that's referencing a sample size. So in this case, our total in the frequency column is the total sample size. It's 120 people that were sampled. What we can do is we want to then make statements about the relative frequency. When we say relative, we mean what is the frequency relative to the total number of people sampled. There's lots of different ways that are good ways to do this. There's one way that I want to suggest to you is probably a pretty bad way to do this. So let's go ahead and fill out these columns here. The easiest, by far the easiest way to state your relative frequencies is to state them as simple fractions here. 6 out of 120 people sampled got the chickenpox below age 1. 30 out of 120 people sampled got the chickenpox between ages 1 and 4, etc., etc. So we can fill out the rest of this guy here. It's not super exciting, and that's good news for you because that means that building this relative frequency column is very, very simple for you right here. It's all just out of the number of observations that we saw. They're all just out of 120. Right? Another good way to indicate our relative frequency is to indicate these as a decimal. So I can go to my calculator here and do each of these divisions. I might need to do a little bit of rounding here, but I can get my decimals out. 6 divided by 120, 0.05. 30 divided by 120, I actually knew this one, that's a 0.25 right there. 48 out of 120, I'm getting a 0.4. 20 out of 120, 20 out of 120. I'm going to have to do a little bit of rounding here now, maybe. I'm getting like a 0.167 right there. Certainly I have a judgment call to be made as to how many decimals to keep. I think it would be way too much to round that up to 0.2 right there, but at least 3 decimal places. If you're unsure about rounding, then at least 3. If you're ever not sure, then go ahead and keep extras. Let's see, 14 out of 120. Again, I'm going to get a pretty similar rounding situation right there, 0.1167. And then 2 out of 120, I'm going to get a 0.0167 here. And so maybe right here, by the way, just keeping 4 digits, since the bottom 3 terms right here, these bottom 3 relative frequencies all had an unending decimal expansion versus these top 3. This is all it was. These top 3 weren't rounded at all. That's just the exact decimal right there. Other ways that we could list our relative frequency rather than as a decimal, all right? So our good relative frequency columns are either a unreduced fraction, a decimal, or the percent that's associated with this. So hopefully we're all familiar. If we want to convert decimals to percentages, then we just have to slide the decimal over 2 places, right? So 0.05, I move the decimal 2 places to the right, and I'm now getting, and maybe I'll just write these with a decimal, 5.0, 25.0%. Here we have 40.0%. Here, again, moving my decimals 2 places to the right, I'm going to get a 16.67%. I'm going to get a 11.67%. And I'm going to get here 1.67%. Now, an important thing to notice here, if I go back to each of these columns right here, is I can go back and redo these same things. Now, notice here, if I added up all these numbers, I got 120. Well, if I add up all of these fractions, if I add, they all have a common denominator already of 120. So down here, I'm just going to get 120 out of 120, right? I have experienced at this point all of the relative frequencies. Similarly here, this relative frequency given as decimals, if you go to your calculator and you add up all these decimals here, I can just do this. 0.05 plus 0.25 plus 0.4 plus 0.1667 plus 0.1167 plus 0.0167. And when I add it up in my calculator, and maybe I can show you here, I did get a 1.0001. I do have a tiny, tiny smidge of rounding right here associated with these 6 sevens that are out there. But it certainly should be the case that these should all add up to exactly 1 right there, representing the entire data set has been collected. Very similarly, if we add up all these percentages right here, we should be landing at 100%, right? So this totaling is just saying, yeah, we accounted for all the data that's out there. Now, what's going to go on in this bad relative frequency column? What's the one thing I don't want us to do here? The one thing that I think makes this harder to understand is if we took all these fractions and reduced them all individually. This makes it a lot harder for us to make direct comparisons from one group to the other. So let me just show you what all these fractions would look like right here. And in fact, you can even have your calculator help you with this if you want. If I do 6 divided by 120 in my calculator, then I can press Math and then frac, and it will convert it to a fraction for me. And it's going to tell me that this is equivalent to 1 out of 20. So the problem with this is that on the one hand, individually, it's completely correct for you to say something like 1 in 20 people that we sampled experienced chickenpox under the age of 1. Completely factual, correct statement. The problem is it gets a lot more difficult to compare it when we get oh, I hate it when it does this. Just leave it as 1 over 4, please. Thank you. 1 out of 4. Making these direct comparisons now gets quite a bit harder. 48 out of 120, that's going to give us 2/5. 20 out of 120 is 1/6. 14 out of 120, that one's going to, let's see, that one's not going to reduce down very much. That's just going to be like 7 out of 60, right? 7 out of 60. And then 2 is just going to give us 1 out of 60. So the problem with this is it makes it way harder for us to make direct comparisons, right? I can see, for example, that this number here, 0.1667, is larger than this number right here, 0.1167. But at a super quick glance, and like I've dealt with math a lot, I'm going to go ahead and say I'm guessing I'm better at fractions than probably everybody taking this class. It's still not super obvious to me at a super quick glance which one of these two fractions is bigger over here, right? So if the whole point of this table is to make it easier for us to understand our data, then what we don't want to do is put ourselves in situations where it's hard to understand our data. So very commonly in statistics, in probability and statistics, it's very common to actually not want to reduce any fractions that we're working with, because it's very common in both probability and statistics that we're trying to make comparisons across two different fractions, and I really want to be able to see an easy, obvious direct comparison. I can easily, obviously see the direct comparison here that the top one is larger than the second. I can easily see in the direct comparison here that the top is larger than the second. I can easily see in the comparison here that the top is larger than the second, but right here, it's not super easy for me to see that this top value is larger than this second value. And so that's just to say, reducing fractions is not necessarily a good thing to do if your purpose with those fractions is to compare two different fractions. If your intent is only to do math with one fraction, then you probably want to reduce it all the way down. But if your purpose for creating a fraction is to compare it to another fraction, it's mostly best if they have the same denominator, and the easiest common denominator for them to would always be your sample size right here. So this is just to say, if you are ever comparing two fractions, you really want them to have the same denominator, and therefore the good news for you is pretty much everybody is going to get jammed up with the math if they have to do this semester, with the algebra, with some manipulations that we're going to have to do. But one of the nice things is you probably don't have to really reduce many fractions at all this semester, because we want them to be with the same denominator here so we can compare across all of them. So notice down here, like technically we're getting to 100% with our fraction down here, but like how do, to do that addition would be terrible versus to do this fractions addition, adding up this column, super simple. I literally just added the numerators because we already had a common denominator. So I know I've shouted at this enough now, but this is just to say these are some good ways that we can do some things. And maybe I can maybe in my table I can indicate this table design layout. Can I do this quickly, easily? Can I shade these lightly? Get a little background of some. Oh, come on, give me more colors here. Oh, okay, well. Going to shade those green and red. That's okay. The good ones versus the bad ones here. This is just to say, don't reduce your fractions if your goal is to make comparisons. Finally, we want to talk about cumulative frequency. These 4 columns that we just filled in are kind of all doing the same job. They're just different representations of doing the same task. 3 of them are about equivalent and good. 1 of them is technically equivalent but bad. The cumulative frequency column, though, is different than all the rest. This is saying, how much have we accumulated? Cumulative frequency, I like to think of the word accumulated. It helps us think about so far statements. How much so far have we seen? So this really matters for an ordering of things. We should notice that cumulative frequency can really only occur with ordinal ordinal categories versus nominal categories, because we want to say so far statements. It makes sense for us to say things like, what percentage of people below the age of 24 have had chickenpox? It doesn't make sense for us to say things like, what people use the modality of driving to car as their modality of getting to work, or less. There's nothing that's less than driving a car, even though I guess in my head I think of like biking as lesser than driving a car or something. But that's a dumb sort of ordering that I'm trying to infer right there. So it matters that these are categorical ordinal variables that we're talking about cumulative frequency with. We have categories that are in order. These are clearly ordered categories because they go from youngest to oldest here. Our cumulative frequency, just as we have these same choices over here, we have those exact same choices over here of the good versus the bad for cumulative frequency. We can certainly use unreduced fractions, we can certainly use decimals, we can certainly use percents. I think that I'm going to go ahead and use the fractions right here. I think it'll just make my life a little easier. I'm noticing that those decimals down there are a bit gross, and I might not want to interact with those decimals, but their fractions are totally nice and clean. So that suggests to me that maybe this would be a good place for us to stick it out with our fractions. So this frequency or cumulative frequency column over here, and maybe I should just bold cumulative frequency over here, the important part. And here we have accumulated so far only the 6 out of 120 that we've seen, right? So this says to me, if you have reached 1 year of age, about what is the probability that you've had chickenpox, and it's about a 6 in 120 chance that you'll have chickenpox by the time you're 1. By the time you are 4, what is the probability that you'll have had chickenpox? Well, it looks like you have a 6 in 120 chance of getting it up to the age of 1, and then an additional 3 in 120 chance of getting it between the ages of 1 and 4, for a grand total of 36 out of 120 chance that you'll have had it by the time up to the age of 4. So a lot of these up to statements, how much so far, how much probability so far have we accumulated? For the next chunk, we're going to get an additional 48 out of 120 probability for the ages of 5 through 14. So 36 plus 48 is going to give us, what's that, 84 out of 120. To continue on, we get an additional 20 out of 120 probability. We're adding on another 20 to our cumulative here to get a 104 out of 120. And again, this is saying, what is the probability that I would get the chickenpox below the age of 24? Well, or up through, I should say, the age of 24, below the age of 25, right? And it looks like we can state our probability as about 104 out of 120 people will get the chickenpox before they turn 25. Okay? Finally here, we can wrap this guy up. It looks like we get another 14 units of probability here, another 14 out of 120 to bring us up to 118 out of 120. And then finally here, we accumulate our last two. So we're going to get up to our 120 out of 120. So some nice things to notice about cumulative relative frequencies here, cumulative frequencies. The first cumulative frequency that you get will always be the exact same as just the first standard relative frequency because all you've accumulated so far is just your first category. The last cumulative frequency that you will ever see in every single table should always be the entirety of the samples that are represented in the table. This should always be the same as the total column for the relative frequency as a fraction, right? So you're always going to start with just a copy of whatever the first relative frequency is. You're always going to end with all of it because otherwise you haven't accumulated all of your data to be represented out here. So in my opinion, I do think like reading through these, I feel like all these whole numbers are very, very nice to me. I feel like decimals immediately get a little bit tougher for me to estimate here. But I think that if I'm just trying to talk numbers, it is nice for me to see things like, oh, a little bit less than 2% of people get the chicken pox older than age 40, or older than age 44, so 45 and above, stuff like that. That's a little harder for me to see as a fraction over here. What I'd like to know from you is if we were going to graph a bunch of this information, then how should we go about graphing this? Should we use a histogram here, or should we use a bar chart for these frequencies, and why? So this is a little bit of our getting into our graphical displays that we talked a little bit about last week, and come up a little bit more this week here. And so the way that we can answer this is we can determine what things are being used here. What was even the variable of consideration here? Well, in our case here, what our variable was that we're collecting, what's the piece of information that we're collecting, is the age at which the individual had chickenpox. And what data type is this variable? Well, when we think of age, we should normally think that age is going to be a continuous variable. Age is typically a continuous variable. But what? But what I can see is that the researchers in this category didn't, or in this experiment didn't, excuse me, the researchers in this study did not quite treat it as that continuous thing, right? If you are 7 versus 9, there is no distinction made in your age in this study. Those both fall in the same range, or I would say here, the same class of data as the 5 through 14 group, right? So what's really happened here is the researchers have taken age, which is typically a continuous variable, and they have, rather than treat it as continuous, they have broken everything down into age categories, right? So even though age is really being collected, it's really sort of like the researchers might as well have asked, which of these 6 age categories do you fall into? And the person would have selected category 1, 2, 3, 4, 5, or 6, right? So again, notice here, this feels like a numerical thing. We are collecting age, but it's certainly being treated as a categorical variable here. We have age categories, but the researchers group all people, all individuals into one of 6 age, and I'm going to underline categories. And so I'm going to think of this as a categorical variable because we have categories of ages that we're experiencing here, right? We're not treating an age as a number anymore. Again, if you are 6 years old and if you are 13 years old, there is no difference whatsoever in those two ages according to this particular study. Therefore, it's good for us to not think of age as being so much of a numerical thing here. Rather, in this study, it makes more sense to think of age as a categorical variable. Since we are talking about a categorical variable, then, we know that we are not making a histogram. Histograms are for numerical data. If we were truly collecting the actual year in which the person got chickenpox, if it was just what was your age in years, then I'd be making a histogram. Instead, because we are talking categories of ages, we are going to use a bar chart. Another thing I think that's really important to notice here is another reason why is this, and here's maybe another thing to think about with our histogram and how this data should be collected. If I were to ask you what is your age in years, that's sort of like me taking age, which is like a time measurement, so it should be continuous, and it's really me making it discrete. Because if I say what's your age in years, then I don't care if you are 6 years and 1 month old or 6 years and 11 months old, those would both be 6 years, right? So in a sense, doing that sort of like making categories for our age also. But here's the big difference. In the scenario where I say just what is your age in years, everything is lumped into a category. I am 6 years old, whether I am 6 years and 1 month or 6 years and 11 months. But the difference is that the distance between all of those age groupings is exactly the same in that sense. 6 to 7, 7 to 8, 8 to 9, 9 to 10. All those gaps are the same. The widths are the same and the gaps between them are the same. Here, we don't have that. This spans 4 years, or right, I guess age 1, age 2, age 3, and age 4, right? 4 years. This one spans 9 years. This one spans 9 years. This one spans what, 19 years? And this one spans an undetermined number of years. So another one of our issues here with trying to think of this as a histogram is that our chunks are different widths as each other. And I don't like that for histograms either. Histograms should be a lot more uniform than that. So these are my arguments as to why I say that these should be categorically considered ages, and categorical data should end up being represented in a bar chart, which does have gaps between our bars, versus a histogram, which does not have gaps between our bars out there. So what graph goes with this? We're going to go ahead and make a bar chart here. And again, our two arguments for why bar chart are, one, the data is categorical. Two, even if you were thinking of ages as not being categorical, the groupings of our ages here are not equally width, right? Our bins are not of the same size. We think about bins for histograms. These bar charts, we don't have that. We're a lot more inconsistent here. So let's go ahead and take a look at what these graphs are approximately going to look like. I'm going to by hand draw some frequency graph and a cumulative frequency graph, and we'll briefly talk about the statements that we make about these two graphs that are different from each other and what type of things we typically expect to see from these graphs. So I'm going to make two graphs down here and compare them, our frequency graph and our relative frequency graph. So I'm going to make our two graphs. So these two graphs should kind of have a lot in common, but the conclusions that we're going to draw about these graphs are going to be a bit different here. So whenever I'm making my bar charts or my histograms, it's always going to be the case that on our vertical axis is where we're always going to represent our counts or our frequencies. Our horizontal axis is, okay, I shouldn't say always, always. Sometimes we make horizontal charts versus vertical charts. Unless I have a really good reason to do that, I pretty much always go with vertical charts here. And so we want our frequencies or relative frequencies on the vertical column here. I'm going to go with my overall frequencies, I think, right here. Notice that these numbers are not too terrible to deal with. We're going up to 120, which isn't some massive number. In general, you should get that, like, if we're dealing with numbers that are like out in the hundreds of thousands or some massive numbers or some tiny numbers, frequencies might not be as good to deal with directly, and we might want to use percentages instead. In this case, because this 120 is a very manageable number, I can easily make visual distinctions between each of these numbers here in our table. That tells me that it's okay for me to just use frequencies in our table. So some things I'm seeing here are the highest frequency I'm going to need to represent in my graph is a 48, and the lowest one I'm going to need in my graph is a 2. So it's really important that I make my graph where both of those numbers are visually easily able to be seen. It's a bit of a stretch to easily be able to see 2 while also stretching out to 48, but we'll do our best here. So coming on over here, I'm going to just label this here as my frequency up there on that axis. And I know that the largest frequency I'm going to see is going to have a height of about 50. So I'm marking that as my upper end up here. I can then maybe subdivide this, and typically what I do when I'm drawing my axes, and by the way, this is a good little bit of graph drawing hints here. Typically what I do when I'm drawing a graph is I pick out what I want my sort of like biggest value that I want to see is. In this case, that's like the 50. And then I'll try and break this down into easy subdivisions, right? So I know that 50 divides by 2 easily to get me to 25. Now, 25 doesn't break down into things super nicely, maybe into 5, so I can try, and 5s are a little bit harder to do, but I can try and break this down into groupings of with 5 here. I think I did not too bad right there. So that's going to be our 5 down here. 10, I've got a 15 for this guy. Try to make this as readable as I can here. There's my 5, there's my 25. All right, 30, 35. I know I've got a 40 coming here, so maybe I'll mark a 40. That's our 40 mark right there, and here's our 50 mark. I'm just trying to make my tick marks for the drawn numbers a little more obvious. So that's my bad job there of counting by 5s. When you do this on your homework and you do this with graph paper, you're going to do this way better with lined paper, or not doing this with a stylus on the digital pad, because my drawing skills here are bad. So let's get our age ranges down here. Also, I know that I've got a less than 1. I know that I've got a 1 to 4. I know that I've got a 5 to 14. I know that I've got a 15 to 24. And I've got a 25 to, what is my other groupings here? 25 to 44, and then 44 and above. And then our greater than 44, so I'll stretch this guy out a little bit here. And now I can go ahead and build my heights here. So our less than 1, we had a total of 6 individuals that experienced the less than 1. So I can go ahead and make my bar that's about 6 units high. A nice thing to do, by the way, on these ones is that you can tell here, certainly that this is between 5 and 6, but I'm doing a relatively bad job. So often what people will do is just count the height on the top of the bar right there. We want to draw the bars to give ourselves a visual sense of a number, but including the number for the detail there is also a pretty good idea. Alternatively, again, percentages are acceptable on this axis. Percentages are also acceptable on the heights of the bars right there. So let's fill out the rest of these guys. 1 through 4, we can see we're getting to a height of 30. So 1 through 4, I'm going to find my height of 30, which is right there. Here's my height for the 1 through 4 bar. 5 through 14, this is our most common category, 48. And I know it's my most common category easily from this table because I can see it in the height of the bars. So there's my height of 48 and the bar that goes with it. There we go, not bad. 15 through 24, height of 20. (25 through 44, height of 14. And finally, our one that we can barely see down here, a height of 2 for that last box right there. So here we have made our bar chart. We've clearly labeled that we are indicating our frequencies, not our relative frequency. If you wanted to use percentages for this vertical axis, totally acceptable. You should just indicate that they are relative frequencies if you use percentages rather than the absolute frequency, the true counts of how much we saw. If you're like me, okay, so here's what I'd say. My bars, I'm actually surprised at how well I was able to draw these bars right here. They've got kind of even equally spaced gaps. They're not all screwy lined right here. I've got numbers on top. And again, notice that if you don't think that your graph is like super easily readable, make it more readable. Remember that the whole purpose of ever drawing a graph ever is just to get a visual sense of the comparison between values, right? So the things I'm looking for my takeaway on this graph right here are things like, I can easily look at this graph now and say, most people get the chicken pox between age 5 and 14, right? What I think that I can do well with my frequency graph is make individual observation statements about single groups compared to other groups. I can say things like, the fewest people get the chicken pox above age 44 as a age category. The most common age category in which to get chicken pox is the age range of 5 to 14. Almost half of all people get the chicken pox between the age of 5 and 14, things like that. So again, what I can do is make good individual comparison statements here. Other things I think I can say. You are more likely to get the chicken pox when you are a very young child than when you are an older adult. I'm looking at things like the 1 through 4 column right here. versus things like these 25 through 44 columns, right? So what this frequency table helps us do is it helps me say I can make direct comparisons between one category and another category. It's comparing individual categories across the data here. The cumulative frequency table is going to tell me something a little bit different. Now, the cumulative frequencies are always going to be, I always like to think of these as cumulative relative frequencies. But in this case, I guess we don't necessarily have to, right? And in fact, we didn't even do relative frequencies. We did cumulative absolute frequencies here. So let's make this second table here and see how it's going to vary a little bit. The thing that's really important here to notice is that we're now measuring out of 120. We're no longer measuring where the largest object was 48. Now the largest object that we need to get up to is 120. So the upper bar for this thing is going to stretch a little bit higher. So in a sense, the graph is going to get squashed down since our same max height is now going to be 120 instead of 48. So I'm going to come over here and, oh gosh, I kind of want to move this here. Can I grab this? Is it going to let me? No, it's not. That's okay. So let's go ahead and mark our highest height over here as our 120. That's everything right there. So again, I'm going to play these halves games right here. I'm going to go with 60 is half down to from 120. Halfway between 60 and 120 is 90. Halfway down here is 30. And maybe I'll just give myself some tick marks for the tens, right? So that's 40, 50, 60. 70, 80, 90, 100, 110, 120. So in this case, all my tick marks are another 10 units that have been accumulated. I still have all of my same categories down here. Less than 1, 1 through 4, 5 through 14, 15 through 24, 25 through 44, and greater than 44. The point of this graph is that we're going to end up making some different observations. The thing that we're going to be able to directly see out of this graph is different than the information that we directly see out of this graph. Like this graph, the biggest thing that catches my eye is the tallest column, the shortest column, and direct comparisons between column heights. We're going to see different kind of information that we get out of our cumulative frequency graph over here. So let's go ahead and fill this guy out. So I know that in any cumulative frequency graph, the first column here is always going to match our regular frequency graph's first column because so far we've only accumulated 6 units. Now we got to be a little careful though because this y-axis is measured differently than this y-axis. So it's true that I want a bar of measure height 6 here, but measuring a height of 6 is a little bit different on these two graphs. So that tick mark is at 10. So this is going to be a very small column here. So there's my height of 6 right there. 1 through 4 is going to give us another 30 units. So that tells me this should be at a grand total height of 36 for the next bar here. So we're going to get 36. That'll be there just below 40. Then there's my cumulative frequency graph with a height of 36. Next up, column 5, age 5 through 14 is going to give us an additional 48 units of height. That should put us at, what did we say, 84. So I'm going to go up to 84 here. Just my halfway between 80 and 90. We should now be at 84. 15 through 24 is going to add another 20, so we should now be at 104. So if that's the tick mark for 100, I'm halfway between 100 and 110 about. So there's my 104. 25 to 44 is going to get us an additional 14, so we're almost all the way there. All but 2, we're at 118. And finally, we get here to 120. So here's the thing I want us to notice about this cumulative frequency graph that's different than our regular frequency graph. Whenever we are accumulating frequency, what we know is that we're always adding on more frequency because we've got another group. At worst, there could be no members of a single category, right? It could have just been the case that nobody we questioned had gotten the chickenpox from age 1 to 4. That would have been statistically unlikely based on the chickenpox, but like in a broad statistical sense, like you could just get no people in a category. In that case, we would have accumulated 0 additional height in a bar, But notice in our cumulative frequency graph, one of the things that we should always expect is that every bar is taller than the last bar, and we're always going to get our final bar to represent the entirety of the entire data set. This is always at a height of 100% if it's in percentages, or it's always at the height that is equal to the sample size, because by the time you get to your last category, you have to have seen all your data, right? So one of the differences here is that notice that this bar graph rises and falls for the frequencies. Cumulative frequency graphs will always only rise. They will only ever be increasing from left to right because we are always accumulating a little bit more. And it might be that they stay flat from left to right, but they'll never dip down, because to go downwards would be to say that we somehow lost some accumulated frequency when we sampled some more people, and it doesn't make any sense to sample one person and have that cancel a previously seen person. We're not getting negative observations, right? So cumulative frequency graphs are always going to be increasing in height as compared to this frequency graph that increased until the most common category, then decreased because these were less common categories. The other thing I want to say about this is that our observations that we make about cumulative frequency graphs are different than the observations that we make about regular frequency graphs. The regular frequency graph, I want to observe things like the age range from 5 to 14 is the most common age grouping, most common category of age in which to get chickenpox. That's a lot harder to see over here, and I can see that we did make our single largest jump in heights from the second to the third column. That's equivalent to this being the tallest column. But what's a lot easier for me to see here is different information. I always like to make statements about so far type of things when I see my cumulative frequency graphs. I think that the observations we should be making about this cumulative frequency graph is things like we could say, almost all people get the chicken pox by the time they're 24. I think that's a good generic observation that we're making here. What we've established here is that this column right here for up to age from age 15 to 24, this says to me, by the time you reach the end of age 24, you have a 104 out of 120 chance of having had chickenpox, right? So I like to make statements here that are cumulative statements. Most all people by this point in time have experienced this. And so these up to statements are a lot of statements that go with these cumulative frequency graphs because we talk about accumulation of probability. These help us make statements about individual columns. Cumulative frequency graphs help us make statements about all the columns we've seen up until a certain column out there. So a little bit different kind of conclusions that we make from each of these. So this is just a small thing. I certainly will ask you on, like a first test or something like, here is a frequency graph and a cumulative frequency graph. Tell me what's the easiest observation for you to make about the data from the frequency graph. Tell me what is the easiest observation for you to make about the data from the cumulative frequency graph. So we make slightly different observations from these graphs. Remember, the job of a graph is to help you get a visual representation of the size of numbers. So it does matter that we properly scale our things on our y-axis over here. But since bar graphs are always associated with categories of information, in a bar graph, we don't necessarily need to worry about our spacing on this horizontal axis being consistent. And remember, this bar is only representing 1 year of life. This represents 4 years of life. This represents 10 years. This represents 10 years. This represents 20 years, right? Like, these are all different widths on the x-axis, but because they're categories, we don't worry about that too much. When we make histograms, which we'll talk about tomorrow, it really matters then that our x-axis gaps are going to be the same because we are measuring a distance on the x-axis in a histogram, but not on these bar charts that we're looking at right here. So I think this is all I was really looking at for our frequencies and our cumulative frequencies right here. We should understand what are good ways to represent relative frequencies and what are bad ways to represent relative frequencies. And all you got to remember is, congratulations, you don't have to really reduce almost any fractions this semester. It's actually not good for us. So in this case here. So and cumulative frequencies, we're always just accumulating what we've seen so far. It matters that our categorical variable is ordinal, has some natural ordering to it so that it makes sense to accumulate the frequencies. If we're talking about like modes of transportation to get to school, it doesn't make sense to have a cumulative frequency because it's not necessarily the case that you should accumulate walkers and bikers before cars. Like those, that's not a natural ordering, right? So ordinal categorical variables get cumulative frequency as well. Okay, I think that's all I got to say about this. And in general, this really is everything that we need from 1.3. Again, I'm not too worried about the levels of measurement thing right there. I'm more worried about our more traditional breakdown of our variable grouping. So we just talked frequencies and frequency tables. We talked about bar graphs and both the frequencies and the cumulative frequencies and what types of interpretation statements we make about these. And here we get lots of mosts and leasts for categories, and here we get lots of overall statements about collections of categories. So there's our section 1.3. So now I'd like to talk about section 1.4. This is going to be much different. Section 1.3 was very much about how should we look at categorical data. What's the best way to represent categorical data in a table? What's the best way to represent categorical data in a graph? That's what section 1.3 was about. Section 1.4, wildly different. We're not even going to look at any graphs in here or any data. We're going to talk more about ideas in this section here. This one's really important, but this is really verbal, so certainly hope you're watching this video, since this is kind of all my words here are really the important thing. So here we're going to talk about experimental design and ethics. And I should say real quick, this is one of those things where when I very first taught a statistics class, these two ideas are very often lumped into one section, and that really bothered me the first time I taught a class. I was like, these things have nothing to do with each other. And it's very obvious to me now that they have everything to do with each other. So first I want to say, like, anticipate these ideas to be very much intertwined right here. So we always want to know why are we talking about something, and I should say to you, you guys should expect this of me. There's nothing that we're ever going to talk about in this class for no reason. There's always a why are we having this conversation type of thing. And very often what I should do to help justify the why to you is to say, what's our goal, either like this week or today or this semester overall, to know why we're doing this. In general, our generic goal this semester is to be able to use data to draw the strongest and most broadly applicable conclusions that we can make. But we also want to be really careful that we don't overstate what we know, right? And that's a very common theme in students taking statistics, is getting a little too excited and being like, look at the statement I can make. And it's like, you better ease off, because maybe we don't have enough to maybe make that strong of a statement. So we want to make the strongest statements possible, but without overdoing it, without making some like wild claim that's not quite true, right? So what we need to know is, how do you do science in such a way that allows you to be in a situation that you can make these very strong claims as opposed to just very weak claims? And we'll talk about these claims in a second. As with so many things this semester, it's going to be easiest for us to just look at an example to kind of get rolling with this one here. So here's our hypothetical situation. Suppose that you're a researcher and you are backpacking through a place you've never been, right? I'm just trying to say we're in some sort of unfamiliar territory here. We're backing through some country we've never been to before, and we come across a small town. And in this small town, you notice that they're immediately next to a nuclear reactor. And you should notice that this nuclear reactor's waste disposal plan is just to dump all the radioactive waste into a local pond. You get into town, you go to the local bar, and you say, hey, what's going on around here? And you read the newspaper or whatever, and it indicates to you your quick survey of the local population, however you do it. You end up finding out that the people in this town have a 6 times more likely chance to develop lung cancer as the country as a whole that you're visiting right now. So the question is, should we be concluding that the nuclear waste is what's causing an increase in lung cancer rates right here? This seems to be a pretty reasonable conclusion to draw right here, that you're around things that are known to be carcinogenic. You're experiencing people that have higher than average cancer rates. Can we say that this nuclear waste is causing the lung cancer rates? And the answer is absolutely not. There's no way that that would be a reasonable conclusion for us to make right here. In this bit of, and I very much am in putting this in quotations right here, this bit of science, there are only 2 variables that we have accounted for as a researcher: the level of exposure to radioactive waste and the lung cancer rates. There could be a ton of other variables that are involved here that we haven't considered yet, and those might be really important for the conclusions that we should be drawing. And so therefore it would be way overstepping our bounds to say, well, these people are getting lung cancer because of the radioactive waste. Now, I'm obviously setting up this situation because that would probably be the case there, right? But statistically speaking, as a statistician, you have no evidence currently that suggests that the radioactive waste is causing the lung cancer rates to be high. What you don't know is about tons of other variables, right? What if, for example, the only thing that the radioactive waste was affecting was their drinking water, and everybody in the town drank bottled water? And further, what if you then found out that every single person in the town smokes 3 packs of cigarettes every single day? Well, at this point, then, my hypothesis is now being updated. Now, if I take into consideration these two other variables, uh, do you always drink bottled water? Yes or no? How many packs of cigarettes do you smoke per day if I find the average is 3? Well, now I'm thinking, you know what? Maybe it's just coincidence that they're next to a nuclear reactor. I think all these people are getting fine, clean drinking water. I think it's actually the fact they all smoke that's giving them the lung cancer rates, right? So what we refer to these as are lurking variables. These are variables that are not accounted for in our research that may or may not have a big impact on the conclusions that we're trying to draw. So one of the things that you should notice here is that if you're trying to do research, what you can't do is just roll up on a situation and be like, wow, look at that variable and that variable. Here's what must be going on. We really have to account for every single variable if we actually really want to draw strong conclusions like lung cancer was caused by the exposure to the nuclear waste right there. So then what your next question should be is, well, that's ridiculous because how do we ever control for every single variable, right? There are literally billions of variables that are going to be affecting everything. And some of them have big impacts, some of them have small impacts, but they're there nonetheless. How do you control for all these? Well, the answer is it's really, really hard to control for every variable. What we can't do is actually control it, but what we can do is we can grab populations to perform this study on that we think have equal distributions of each of these lurking variables. Right? So let's talk about that distinction here. In this case, if you are the backpacker that just walked into town and attempted to conclude that lung cancer rates were high because of nuclear waste exposure, then what you just did is you just performed an observational study. In observational studies, you as the researcher have no control over anything that's happening. All you're doing is recording data. You just walk into that town, all you're doing is just recording the, maybe the age of the people at which they get lung cancer and recording maybe how long they've lived in the town. But you can't say to somebody, hey, you get more radiation, you get less radiation, you move out of this town, anything like that. You have no control over anything. You are simply an observer. So this is an observational study. And you should notice that this is really what's preventing us from making any strong conclusions. Since we don't have control over these lurking variables, we don't know really what variable might be causing the difference in lung cancer rates that we're seeing. So suppose that we did want to prove this, though. What we want to do is we want to prove that this nuclear reactor and its radioactive waste is responsible for the lung cancer rates being so high. What could we do to prove that that would actually be the case? Well, what we need to do is we need to control for all of those lurking variables out there. We need some way to be in control of that so that we know as the researcher that there's only 2 variables that are changing, the exposure to radiation and potentially the incidence of lung cancer. That if we can narrow it down to just those 2, then we could know if one of them caused the other. And so our definitions here are an experiment differs from an observational study in that the researcher does have control over the experimental units, in this case the people, and the treatments, in this case the exposure to radiation in an experiment. In this experiment, in every experiment, we have explanatory and response variables. Here, the explanatory variable, the variable that is going to explain the changes that we're seeing, is the radioactive waste. It is expected that the amount of radioactive waste exposure will explain the increase in lung cancer rates. The response variable is the thing that's changing in effect relative to the explanatory variable changing. In this case, it would be the lung cancer rates. We believe that lung cancer rates are high in response to the exposure to the radioactive rays. So this is our cause and effect variables right here. What's causing the change? What is the effect based on that cause? Explanatory response variable. So if I wanted to really prove that we're going to be seeing that the radioactive waste is causing this change in lung cancer rates, then I need to control all other variables. Here's the way I could do this. I could select a simple random sample of 1,000 citizens of the country. I'm just making up the number 1,000 right there, but I want to do a good science here, right? So that's a pretty big size study. I could then tell all the people, oh, there's my step two, I'm jumping over there. Step two, I could randomly choose 500 of them, and I would say to them, 500 of you, you need to go move to the city that's next to the nuclear reactor. And I could tell the other 500, keep not living next to the nuclear reactor, right? If you don't, keep doing it. Or maybe if you currently do, move away, right? After X number of years, we could determine the lung cancer rates that are associated with each of the groups. So in this case, what did we do? Well, we took all of the participants, all 1,000 participants, the entire sample, are divided randomly into two treatment groups. The two treatments here that are being applied to each individual experimental unit in the study are the treatment here is you either live near the nuclear wastes or you're being given the treatment of don't live near nuclear waste. Those are the two treatments that are being given. Notice that in every experiment, one of the treatments is sort of like don't be given a treatment, right? So don't just think of treatment as like literally you took medication. If we're trying to see if a medication has an impact or not, it might be that three treatment groups are no medication, a 5 milligram dose, and a 10 milligram dose. Even though one group is not receiving any medication, statistically we still refer to that as one of the treatment groups, where the treatment that you received was no medication, right? So even if it's the nothing group, that's still a treatment group by definition. That is the group that we refer to as the control group. The control group is the treatment group that doesn't actually receive any of the explanatory variable, right? In this case, since the explanatory variable is be affected by nuclear waste, the 500 individuals that don't live near nuclear waste, those are our control group, the group that we think should not differ from the broader population. Some other words that we should have associated with this, they don't quite apply in this context, but we can bring them up in the sense of any experiment. This is not a blind study. In a blind study, the people that are being receiving the treatment do not know what treatment they are receiving, right? So if we're talking like the book talks about with medications, in every medical study where a medication is being given, there will always be some people that are truly given the medication, some people that are not given the medication but are told that they are given the medication, and then some people that are just truly honestly given nothing, right? So you hear of sugar pill in like every single medical ad on TV. That's the placebo. That's the pill that looks the same as the actual treatment, but literally just has like a little bit of sugar in there. It has no actual medical anything in it, right? So all medical studies, it's really important that they're blind because they want to control the effect of placebo. In this case here, it would be really weird to have a placebo. That would be like tricking somebody into thinking that they're living in the nuclear town when they really don't. I think it would be hard to convince somebody of that. So in this study, it's not a blind study because all the researchers know which city in which all the individuals live in, and the individuals know which city they live in. They know if they live in the nuclear waste city or not. So nobody is blind in the sense that everybody knows what treatment group they belong to. Both the researcher knows and the individual knows what treatment group they belong to. There are no placebos in this study because nobody is unsure of whether or not they're in the treatment group or not, right? A placebo is when we say, here is the pill. You're receiving the medication. Even though you're not, that would be the placebo. We don't have any of that in this case right here. And by the way, back to the blind thing. I brought this up last week. Double-blind studies are when the researchers also don't know which individuals have been given the treatment. Last week, one of the things that I told you about was this pre-bias that researchers sometimes go into their studies with, saying, I expect the people that take the medication are going to have lower cancer rates. Well, having that expectation going into the study can cause you to do very subtle things that might tip the study's results incorrectly in the favor of a certain result. So double blinding a study means the researcher isn't even sure which treatment the individual is receiving. So he's sort of randomly reaching into a bag and it's going to have, choice 1, 2, or 3. Real pill, sugar pill, no pill at all. And that will be randomly assigned to a random individual that he doesn't know which individual it is. Later, after the study, they will connect what treatment was given to what person, but we don't want to know that along the way because that might cause us to have some bias about the way that we run the experiment. So being blind in studies is really effective way of proving to other people that you were not biased in your research because you had no idea about what outcomes should have been associated with which treatments because you don't know what treatments any individual receives. So blinding your study helps convince other people it was legit. It's a good way to prove that one type of bias was not involved in your study. So, what else do we think about this study, right? So, the good news about this study is that this would totally work. If we performed this experiment of taking 1,000 people and putting 500 in the nuclear city, 500 not, we could probably 20 years later measure their cancer rates. And I bet, given that we know that nuclear waste does cause things like cancer, I don't know about lung cancer specifically, but we would certainly expect that after 20 years, if there truly was a cause from the radiation to the lung cancer, that we would see a much larger percentage of lung cancer rates in the 500 that were there versus the ones that weren't. The very obvious problem with this study is that we can't do this to people, right? That's just not a thing that we can do. The bad news is that this is super unethical. So the important thing to see here is that while sort of part of the purpose of this unit is for us to discuss the distinction between observational studies and experiments, the really important thing to understand is that very often as a researcher, you want to always do experiments. Experiments will always lead to you being able to make stronger concluding statements than an observational study. But most of the time, experiments are super unethical because you're intentionally causing damage to people just to see if you're causing damage. And it's not just to people, right? It's the environment, it's animals, it's other things. Very often, our limitation is that we can't perform experiments because there's ethics getting in the way, right? So what's our big takeaway here? Well, one of our big takeaways here is we can only establish cause-effect relationships between two variables if we perform an experiment. Observations will never allow us to make cause-effect statements because when we perform observational studies, we are never controlling for all the other lurking variables. In an experiment, we assume that all of the lurking variables exist in equal proportions between each treatment group, and therefore we should have equal amounts of people affected by each lurking variable in each of the two treatment groups. In the two treatment groups, the only thing that should differ is are you being exposed to nuclear waste or not? That should be the only difference between the groups. Observational studies can only show us that two variables are related, but they can't show us that one causes the other, right? And there's a big difference between two variables being related and one causing the other. Most data that we desire, like in the universe, is very difficult to collect due to ethical concerns, forcing us to perform observational studies rather than experiments. And I shouldn't even just say ethical concerns, that is one of the biggest chunks like on Earth, but like if you're a physicist, if you're an astronomer, well, guess what? It's really hard for you to perform experiments on stars. You're literally just praying that something goes supernova within your lifetime that you're going to be able to observe. Excuse me. You're going to pray that something goes supernova a couple billion years ago so that in our universe it's observable in your lifetime. Otherwise, you don't get to kind of see that stuff, right? Like, there are lots of different categories of science where we don't have the opportunity to do an experiment. If you're a geologist, actually, technically, we're actually probably okay at causing earthquakes by now. But again, that's something where you just got to kind of wait for one and observe it. You don't ever get to apply a treatment group to see what kind of impacts you get, right? So lots of data that we want in the universe is very difficult to collect because we can really only do observational studies rather than experiments. And again, on Earth with humans, most of the roadblock there is ethics, or with other animals. Right? And my examples are, we could probably find a cure for cancer pretty much in the next year if we really, really wanted to. All we'd have to do is give every researcher, every medical professional on Earth permission to just give cancer to people at will so that they could perform all the experiments necessary to try out a bunch of different treatments. We pretty much have decided as a species that we do not believe it's worth just sacrificing hundreds of thousands of people's lives randomly so that we can gain this information. So we don't do it, right? All we can do is observational studies with these things because it's never going to be ethical to just give someone cancer to see what we do with it, right? So we're limited by ethics right there. It's forcing us to do only observational studies. That means that lots of cancer research ends up only making much weaker conclusions where we can't make as good of causality statements at the end because we didn't do an experiment. We only did an observational study. Even observational studies can end up being very invasive, right? If I say to you, how old is that sequoia or how old is that redwood? You have one good way of answering my question, and that's to cut it down and count the rings. In that case right there, you have to destroy the object to study it. And that's the case with lots of other medical things, right? If you want to really understand the brain work, how the brain works, well, a nice thing to do might be to cut open a person's brain and poke around in there. You're going to probably kill the person along the way. You might have learned something, but we have agreed as a society that the gain in information is not worth the loss of life along the way. And so recognizing, and by the way, I should also say, this is, our viewpoints on these things have obviously changed over time, kind of a lot. It used to be very, very common. Here's your word of the day. Pithing, P-I-T-H, pithing is the act of essentially beheading a frog that's still alive. It used to be pretty common back in the day for people to do, high schools to do labs where you experimented with the spinal cords of frogs and you could pith the frog, which would be to cut it at its spinal cord right there, and then poke each of the individual nerves and see each of the legs, control each of the 4 different legs. This is a pretty common lab experiment that used to happen a long time ago. And it's turned out that people, at least in the US, I'm not going to try and make too broad of claims here since that's kind of our theme today, but it turned out that a bunch of people have decided that we really don't think that's cool anymore to just deliver 30 live toads to a class and there to be 30 dead toads at the end of class. So that's a thing that we've phased out, right? So it's also true that ethics, I think, are something that are a little bit more permanent rather than just like a cultural change over time. But things do change still, right? So we do have these kind of changes in what we consider to be appropriate scientific things or not. And part of the other reason we've gotten rid of the whole frog experiment is because we've figured out better ways to do things. Students still do this frog experiment in a sense, but often it's done digitally now, where you're going to get a really good look at one of these in a lab or something like that, rather than all these students killing all these frogs, which we might not consider to be an appropriate thing to do anymore. So again, we want to make this distinction between observational studies and experiments. We get to make very strong statements from experiments, only weak statements from observational studies, but we often can't do experiments even though they're better because we're often limited by literally not being able to perform an experiment because you're an astronomer or a geologist, or ethics concerns limit us and prevent us from doing that experiment. It's only responsible of us to do observational studies. In an observational study, the types of conclusions that we make are conclusions that sound like the variable x is related to the variable y, and we can prove that they are related, but we cannot prove that changes in one cause changes in another. In experiments, we do get to draw those conclusions. Changes in the variable x caused the change in the variable y. So it's a much stronger conclusion. We really want to establish causality, but we also want to make sure that we don't overstate what we know this semester. So a very common mistake for a student to make, and something that the internet loves to talk about, is the fact that correlation does not imply causation. Correlation has that word in its relation right there. So this is saying just knowing that 2 things are related does not imply that one thing caused the other thing. Right, so let's look at some of the examples of that right now, and this will be our wrap up for today. All right, let's look at these 3 verbally, and then we'll Google around for some funny pictures on the internet. Statements 1. Windmills spin faster when more wind is observed. Therefore, windmills create wind. Right, there's our causality conclusion based on the observations. We know that this is backwards. Wind causes windmills to spin. Windmills spinning don't cause the wind. That's kind of funny because to mill something sort of means to create it. So windmills sort of sounds to me like you're creating wind. But that's a backwards conclusion right there, right? About which we want to state X caused Y. Here we falsely concluded Y caused X. Number two, I often have a headache when I wake up after sleeping with my shoes on. Therefore, sleeping with shoes on causes headaches. Some of us, particularly those of us that may have just completed a more traditional college freshman year last year, may be very familiar with this attempt at cause and effect right here. My college experience very much led me to believe that this conclusion is true. However, I eventually learned after several years of college that it was not, in fact, my shoes giving me the headaches. It was the fact that I was drunk and falling asleep with my shoes on. And so here there's a lurking variable that is called alcohol. That is the relation that is kind of connecting this idea of sleeping with your shoes on and waking up with a headache, right? So this is our lurking variable here of alcohol that was causing us and not acknowledging the lurking variable is causing us to draw a false relationship between two variables there. Number three, when ice cream sales rise, so do drowning deaths. Therefore, ice cream sales cause drowning deaths. This is another example very similar to number two. Just because two things are related does not mean that one is causing the other. There's probably a third variable that is related to both of the things that's actually the more closely associated cause here. In this case here, and by the way, statement number three, totally true. Well, it's okay. Statement number two is totally true too. Statement number three, this is true because in the summer, people buy more ice cream. That's a fact. It's also true that in the summer, people swim more. And it's also true that the number of hours that a person swims is very closely related to the probability that they will die a swimming death. So number three is valid. There's just a lurking variable. The conclusion's not valid, but the observations are valid. There's just a lurking variable that is going to actually help explain the more correct relationship between these. So finally, last thing I want to do here, give me 5 minutes of your time so we can laugh about some funny things on the internet together and we'll call it a day. The internet absolutely loves the idea of the relationship between correlation and causation. So let's go see some of these funny things on the internet right here. So I'm going to pop over to my browser window here and let's go take a look at some of these things. So all I'm going to do is I'm just going to Google here correlation, causation, and that's all I'm going to Google. And when I Google this, let's zoom in my Googles a little bit right here. One, you can go check out this Wikipedia page right there that lists a bunch of good words. But what I'm interested in seeing is all the great graphs that people have made. And right away, what you can see when I go click on images here is there's a bunch of graphs that have a bunch of related things. So let's look at a couple of these real quick here. And what I'm going to want to do, let me adjust my window a little bit right here. So what you should be seeing here, I'm going to make this even smaller. So I can drag it out more here. Here we go. It's under the heading spurious correlations right here. Here, the observation that we're seeing is that the number of people who drown by falling into a pool seems to be pretty closely correlated with how many films Nicolas Cage appeared in. We can see these two graphs are following each other pretty close. This goes back to 1990. I know you guys can't see that right there. 1990 through 2000, it seems like those were pretty closely related. Now, it's actually the case that I could believe that Nicolas Cage appearing in films is causing people to drown themselves in pools, but I don't necessarily think that that should quite be showing up that significantly right there. Even more closely related here, U.S. spending on science, space, and technology correlated with suicides by hanging, strangulation, and suffocation. Look at how close those two things are right there. I'm certain that they don't have much to do with each other right there. Right? Some other good ones that I'm looking for here. Now, where's the one I really wanted right here? Is it going to make me like kind of actually scroll and search for it? Let's see here. And so many of these they make about drowning. It's a little concerning here. Rates of mozzarella cheese consumption versus civil engineering doctorates awarded. Very closely related. I'm certain that one of them is not predicting the other here. So let me find the last one I want to show you right here. Oh yeah, by the way, one other one sorry, my last serious one that I want to show you right here. This is always a good one to look at. This one is closely associating organic food sales with autism. I think that this one is an ironic one to show. You guys will see that I am asking you to do some super light reading about anti-vaxxers. This is some more things about problematic studies that have been done that have caused people to draw wildly wrong conclusions. I appreciate this graph right here because it's pretty typically the case that most of the people who are claim themselves to be part of the anti-vaxxer movement are obsessed with having all the healthy food. And I'm not saying there's not healthy things that are associated with organic food sales, but I do laugh that staying healthy and only putting healthy things in your body is actually associated with increase in autism. Now, are these correlated or is there a causation here? No. What's been uh, relatively well documented in the last 20, 30 years is that our increasing awareness of autism is causing more people to be uh, documented with that disease. It's not that fewer people had it, it's that we knew less about it. In the year 1800, how many people were getting diagnosed with autism? The answer is zero. Does that mean that nobody had autism? No. So awareness of the disease is part of the factor. Is the only factor that I'm aware of that's causing increasing numbers of autism rates per year. Simply awareness and more people getting tested. So this one just makes me laugh that it's tied to organic food sales that's out there. So let me go ahead and bring up the last graph that I want to show for the class here. And this one, by the way, so one of my favorite websites here, XKCD, and you should see that the very first thing that popped up right here is just a single standalone comic. I used to think correlation implied causation. Then I took a statistics class, and now I don't. Sounds like the class helped. Well, maybe. This is one of those devastating situations where I feel obligated to explain the joke here. I'm sorry, I'm going to explain a joke right now to finish class. The person used to think that correlation implied causation. The person then says, I took a statistics class and now I don't. So the two pieces of information are, I took a statistics class. I don't believe that correlation implies causation. The second person, the person with the long hair in the comic, then attempts to assume that the reason that the person no longer believes correlation implies causation is caused by the person taking the class. That is what the joke is in this, is that we shouldn't assume that there is a cause there. That's why the first person says, well, maybe, because the person does not want to assume that the reason that they no longer believe correlation implies causation is because they took the class. So this is a meta correlation implies causation joke right here, saying it is not necessarily the case that taking the statistics class caused me to no longer believe that correlation does not imply causation. So a two-layer. So there you go. Enjoy me explaining a comic to you as the wrap up to our video today. I know that's bad. XKCD, by the way, has tons of great math jokes and stats jokes. Very often they will hopefully make you chuckle like this. I'm sure I'll bring up a couple more of them this semester because this webcomic is well known for hitting it on the head for lots of math and science things out there. So correlation, causation, let's not overstate what we know about these things here. So to wrap it up, I think that's all I got here. To wrap it up for the day here, tomorrow we are going to talk sections 2.1 and 2.2. We're going to talk a lot more about histograms, building proper histograms. I'm going to make a histogram in Excel so you guys can see that. That'll be sections 2.1 and 2.2. We will conclude our chapter 2 the following week. So today it was sections 1.3 and 1.4. Tomorrow I'm going to do sections 2.1 and 2.2 at our same time slot right here. I think our homework should already be posted for the week as well and all that stuff. So be in Canvas, checking out all that stuff. And I will see you guys tomorrow to talk about 2.1 and 2.2 or whenever you're watching this video. See you later, guys. Have a good one.